Murthy has joined.
Great.
I'm here. Good evening, everyone.
Good evening, sir.
Just we are having a very nice thunderstorm with like cool breeze, and also I didn't want to. So it will create a lot of noise, so I just muted my mic.
Good evening, sir. Dr. Devra here.
Good evening. Good evening, Dr. Devra. Good evening, Dr. Babu.
Good evening.
Good evening, Dr. Mehta.
Good evening, sir. So you are at Indore, no? IIT Indore.
Yes, I just joined Indore in December, like 4 months ago.
We met during ISA convention.
Yes, definitely. I was planning to come to CIAE, but because of the COVID, I mean, once this is gone, I'll definitely visit. And likewise, you should please think of coming to IIT Indore.
Welcome to Vijay Institute.
Yeah, we don't have ag engineering here, so we should start something. So
yes. We may think for working together.
Yes, definitely.
Some area.
Yeah.
Good morning.
Yes, please.
How is Indore now?
It's pretty good. I mean, in the sense that
he is asking regarding COVID.
Yeah, no.
That's
I mean, in the sense that they're basically they're controlling it very well. So you might see the impact of this in next 2 weeks or so. So because it takes that long for it to. So all the responses that you are seeing right now is what happened last 3 weeks, 2 weeks ago. So slowly it will be controlled, and they have been very strict about the lockdown and things like that, and things are slowly improving. So hopefully,
because India learned basically from Indore and Bhilwara.
Yes.
The hot spot.
Bhilwara is now all right.
Bhilwara is also all right now.
Moving fast.
Yeah.
Oh, sir, basically these two hot points were there, Bhilwara and Indore.
So
Indore,
maybe second or third after Mumbai.
Yeah. And what you're actually hearing on news is only half the thing. I mean, we have many more unreported cases because many of them are asymptomatic, and they were limited. They had limited number of testing things. It was not because of lack of testing kits. It was lack of personnel. So some of my colleagues from my department actually are going out and actually running the tests like in the night, so that they have 2 shifts, and then some of the faculty members are going there in the night shift to run the samples.
Well,
and try to help out as much as possible.
Good evening, Professor Singh. Good evening, Professor Singh.
Good morning. Good evening.
Good morning.
Good morning.
Good morning.
Good morning, Dr.
Good
Syed.
morning for him.
Yeah, good morning.
Good evening, sir.
Good morning, Singh sir. Good morning. Good morning.
Good morning, sir.
We'll have a couple of minutes people talking, so we'll have another couple of minutes. We talk to each other, please.
Where did Ganesh go?
Ganesh here.
Hello, Ganesh ji. How are you?
Hi, how are you? Good to see you.
Yes, nice to see you too.
Yeah, that's the advantage of working from home. Just get onto the table from the bed.
Early morning for you.
And if you strategically place your camera, you can still be in bed.
Yeah. That's the advantage.
I thought he will join only at 7 o'clock because he already given speech at 7 o'clock.
Yeah, I thought I'll watch the other one also, so that would be great.
That's good. That's good.
Because of your schedule, we had actually, planned your presentation after 7. As per your.
I thought I'll get some allowances time so that I don't get late.
Welcome and greetings.
Okay.
Thank you.
Dr. Indramani, I think you can invite the people. You can invite the people, then I'll take it.
Okay. So, Professor Singh and friends, this is the 8th day of this webinar series, successful 8th day, and I'm happy to inform that my team told me yesterday that we have 982 Facebook friends. So this is, this hard work of the team, bringing glory for this program. And today we have reversed the program. So first we will have training by Dr. Syed, followed by a presentation by Sangeeta Chopra, my colleague in the division. They will be speaking on solar refrigeration system, gridless, batteryless, automated completely. And then we will listen the great talk by Professor Bora. So this is the plan today, reverse, because we were thinking daily we were having training in the last. So we thought let us have training in the beginning. So with this, I request Dr. Syed to start training part. Dr. Syed, please.
Yeah, thank you, Dr. Indramani. Thank you all of you for patiently listening to me for last 7 days. Today is the 8th day. We have another 2 more days to go. But beginning when I started, I think everybody was a little bit worried about the electronics and embedded, how we are going to learn. But yesterday, I think people were a little bit happy. They told me they could get to the conclusion how it is going to work out. So yesterday, what we talked about is what are the input outputs you require from a microcontroller. For example, relays, switches, displays, motors, and we also talked about the valves, like for example, irrigation solenoid valves. And we also thought about what we require right now in agriculture engineering to concentrate on developing this type of input-output devices. Then we talked about different sensors available. Actually, as I told you, this is only for introduction to the people to enter in embedded, because I see a lot of difference in India. I'm not in academics and I never was in teaching profession till now. And I could only teach my staff for training and everything who are mostly electronic engineers actually. But there is one change I found. You see, when I was in Germany, my professor, Stroppel, he went for 5 years to be the CEO of Fen Tractors. So from the university, my professor went to Fen Tractors to be the CEO, Geschäftsführer. And we got from Dr. Busse from Class. Class is the combined harvester company. He came to university. I asked the question to the people listening now, all of us, will any industry today will take any professor from, and how many professors will be taken by the agricultural industry? Same way, vice versa. We have to think, we have to improve on it to go into the technologies very fast. So it is useful we get outside. With this outset, I start my presentation now for today. Today we'll be covering about, after the input sensors, we'll cover about what is the connectivity and what is the networking, which is the most important today. In the technical day, what we are sitting with cell phones and people are talking, we're going to listen about big data, we talk drones. Connectivity is important, so we should understand what we should learn. So we will start that now. Okay, we are going to talk now about wired connectivities, which are using wire. It looks, don't worry about how it sounds to you, numbers, we will learn that. And we are going to talk about RFID, which is an important feature. And fortunately, I'm spending about 25 years of my life in RFID. And we'll talk about wireless connectivity, where we talk about all types of wireless to understand. The whole thing will be understanding. For example, I personally have worked in almost all the technologies here, including the satellite. Also, we'll talk how to transfer data through. And then we'll come to the protocols which are used only from the controller level, what you're talking. You remember day yesterday we talked about a microcontroller we require. Then we require to find a programmer for the microcontroller. Then we have to find a programmer for the cloud level. Okay, cloud level we'll go tomorrow. So till that time we'll see today. Before going to that, yesterday I was in a hurry when I completed GPS. I have to explain this to GPS, I thought, probably because many people don't know exactly in India. So I will explain you some features. Those who know, okay, no problem. Those who don't know. Now, in GPS, normally for position finding it out or to an extent for spraying also. The laser guided sprayers also in US, which are USD approved laser guided sprayers. Recently, I read about them because I actually was interested to work on them. So they don't use a normal GPS systems. Okay, there are the affordable GPS, normal GPS system, which I see first. Then there's an advanced GPS system which can be used for precision planting, movement of tractors. For example, in US, John Deere and big companies are doing automatic driving. So those types of more accurate GPS. The first affordable GPS we have, is we are getting about 2.5 meters accuracy. The location we can get today in India. If you ask me the cost, maybe around 500, 400, 500 rupees a GPS device, 600 rupees, less than 1,000 rupees. You get the 2.5 meters accuracy, up to 50% of the data. So you will get, for example, 1 data per second. So 50% data belong to 2.5. Rest of the data, how much it will be? Once in a while, it may even go 50 meters, 100 meters. So there are techniques we use to ignore the data. Random, suddenly one spike comes, we ignore it. Sometimes you'll find your vehicle is standing in South Africa also. So we have to ignore that a little bit. That is possible in the software we do it. So this is good enough accuracy for most of the agricultural applications we are using. Now there is a question in India comes and asks, you must use IRNSS, which are Indian satellite systems. GPS is actually global positioning system, which is done by US government. It's almost 40 years, 35 years back, somewhere around that time. And they started with accuracy. Before 10 years, it was 10 meters accuracy when we started using it. Then 5 meters accuracy we used to get. And till now, our Gagan or IRNSS has not reached the 2.5 meter accuracy till now. We'll come to the detail. If somebody is interested, I will explain the detail. GLONASS is the one which is also we are getting in India. It's from Russian satellite system. And we also have Europe, we don't get Galileo system, we don't get in India much. Baidu, we get a little bit in Chinese system, but normally Indian, most of them use either GPS or GLONASS. And Gagan or IRNSS comes recently only. They are slightly expensive. You have to spend maybe around 1,000 rupees around that. Now, second one is coming, assisted GPS. They're simple to understand for you. Assisted GPS means your Wi-Fi system is there nearby. So the Wi-Fi system says, is nearby this place. So some assistance you are getting from different type of existing wireless networks or whatever maybe. DGPS is called differential GPS. So now differential GPS means actually GPS is how it works. I think we all know there are satellites on the top and they are sending signals. You call pseudo random number, PRN number. It's called pseudo random number. So he sends a random number to me actually. But because random number sequence, I know next number what is supposed to come. So he sent me this, I sent this time. Then when I receive that next one, I know what is the time difference. So I know exactly from this satellite, this much time difference it took me. This time difference is in come in microseconds because it's the speed of radio waves, is speed of light. Okay, it's not sound. So less than microseconds almost. Now we are getting second satellite, same. How much time it takes? Third satellite. Then we try to find out all the 3 coordinates and find out the exact location where I am. Normally, you require 4 to 5 satellites view to get a fix, but to continue measuring, you require about 2 to 3 also will do. And RTKS, real-time kinematics. This signals time, which is coming from satellite, is influenced by the weather, ionosphere on the top. So, it's cloudy weather, whatever may be, you will find time difference slightly more or less. Okay. So what I will do, simply I have to find out, for example, I have nearby 2 kilometers, I got a place fixed, I know exactly what is that long, I know it for sure. So there I put a sensor, a GPS sensor and sense it, how much it is. That shows variation. And I am nearby, let's say 500 meters nearby the place. That gives me variation. So it's logical for me to accept similar variation where it happened in the fixed place where I know the location, might have happened also in my place, in the rover where I'm moving. So that adjustment is done. This is a gross idea how the RTKS works. So it requires ground station, a lot of ground stations, and your vehicle is moving. In the different ground station, you get information. India, we don't have so many ground stations installed. Okay, now this is Pondicherry one is there. I mean, many, actually there's a problem where you're not bothered about this till now so much, like in the US, for example. They're not used for agriculture especially. So this is one area we have to work. So now you understood the GPS. Many people talk to me, GPS, GPRS, GPS, GPRS. This is a common sense, people don't know technology. GPRS is nothing to do with GPS. GPRS is only the data packets sending. That is nothing with the GSM only it is supposed to do. GSM is GPRS. Fine. We come back to the next one of the really our connectivity, wired connectivity. The first one we see a 4 to 20 milliampere transmitter. This is two wire. You have a two wire and it goes to some flow. Normally you get flow valves are connected in industry everywhere through this interface. One wire is going, one wire is coming. Power also going through that wire only. Power also going through that wire coming back. And then here, because this, what is the meaning 4 to 20 milliamperes? When it is connected, this circuit will conduct 4 milliamperes. And whenever the flow variation of flow is there, it can go up to 20 milliamperes. So my flow is, for example, 1000 liters per minute. Just an example I'm telling. So that means 20 minus 4, that is 16 milliampere is equivalent to 1000 liters per minute. So that is how I have to calculate back. So this output is coming as milliamperes. I put a resistor here. So milliampere becomes automatically multiplied by resistance become volt. That is a Ohm's law, which we study in schools, everything that you can reference afterwards. So we get a voltage. So we have to use AD converter, which we saw already. Which types of devices is available to you in agriculture also now, as of now, today, in the international market, is pressure sensors, flow sensors, temperature transmitters, your weight sensors, water level sensors. These are all come with 4 to 20 milliamperes. There is no problem in using it, absolutely, but you have to be careful in taking precautions of lightning, which we talked. These are also, you remember they had problem, lightning, secondary lightning only we can protect. Secondary stage of lightning, which is after effect. Lightning happens somewhere 1 or 2 kilometers away, and the effect is coming for you several 100 meters, let me say 1 kilometer away. Now here you're getting a secondary effect that you can block with those gas discharge tube, for example. I told the example that we'll take. This is an excellent one actually you can use in the field if you take precautions of it. And the noise is very less. Now next question people ask how much distance you can go. 1 meter to 5 kilometers you can go. Okay. So this is one of the, when you buy, why I'm telling this is to when you buy sensors or something, you must consider this. This if it's available 4 to 20 milliamperes, easy to interface. Fine, that's all. That's the idea. Long distance, reliable communication, power and data, the same wire. Okay. Next one, we go to serial, okay, connected. That is RS-232, which we saw 3 days back, which our terminals and all olden day connected. We know that RS is serial. RS, normal TTL serial is actually, it is 0 to 5 volts. And when you talk about CMOS chips we use today, 0 to 3.3 volts or 0 to 3 volts. When you use Arduino, normal Arduinos, they are 0 to 5 volts, for example. But you see, I told you, when you want to connect two places together, you use a pipe, water pipe. Same you connect resistor here, a wire. A wire has resistance. So it will drop the pressure, it will drop the voltage. So when I use only 5 volts at one end and draw the wire for, let us say, 50 meters, where at the end of it, I will get only probably 2 volts or 3 volts, so which is not acceptable. So I try to make it plus minus 12 volts, very high. So here is my sensor, for example. I make this signal send here. I again convert to 0 to 5. This is called RS-232 standard. This is very standard. So you can go RS-232, you can go, normally we'll see the distance, few meters, but you can even, well planned, you can go up to 30, 40, 50 meters also when you use shielding and stuff like that. Now, one device is transmitting, that will go to another device receiving, one device transmitting will come to another receiving. That's all. You have handshake protocols and all, don't worry about all these things, right? Then you have another one called LIN bus, which are used in automobile very clearly. Probably it will come in tractors and equipments also in the future. This is, you see the previous screen, RS-232 we told, transmit from here this direction. This is receiving one dedicated wire. From here, one dedicated wire transmitting that will receive. So 2 wires required, one common wire. Okay. Now, instead of these 2 wires, use only one wire. Use only one wire connecting. Okay. Intelligent way of one wire connecting, and they will switch automatically. He will either talk to him or he will talk to him. One wire, they will exchange each other. You put a protocol inside. For example, right now also, now you're all listening to me only one wire communication. Now I say Dr. Indramani, he will reply me. Others all keep quiet still. So one wire we can communicate like this with many people. Okay, that is a bus, what we call as a bus. Now this is used in automobiles for wherever motors are there. Door car, you click everything door, wiper movement, window control, up and down. These are all using the LIN bus in automobile. So with single wire, very easy, no problem of shorting, nothing happens. So this also is not, I don't know right now, in fact, it's not come, but it will come. Next one we think about is the long distance communication when you want to use. This is RS485. Can you control the mic, please? RS485. Now, one data we have, for example, 12 volts or 5 volts we are sending through one wire. Nearby, if there is a noise, some noise in my motor is running, it will jump a spike on that. So 5 volt becomes sometimes 12 volts. If there is a negative spike, the 5 volt become minus 5 volts. So data will get lost. So what do? We use 2 wires for one wire. For TX transmission, I use 2 wires from me to, let us say to Indram, to all of you, 2 wires I use. So in that, if I want 0, one wire I make 5 volts, another wire 0 volts. If you want to transmit one data, I reverse the polarity. So this way noise comes, it comes both the lines. So suppose I'm transmitting data 1, which is the first wire is 5 volts, second wire is 0 volts. If the noise of 5 volt comes, at the end I will get 10 volt and 5 volts. So if a difference I take, is still 5 volts only. So it's a differential balanced transmission. This is one which is very, very useful, and they are used normally wires twisted pair, the way like that. 2 wires are used. So one data will come, one, for example, transmit data, it will go to 2 wires, it is actually going, divided into 1, instead of 1, it divided 2. So noise, this is common mode CMRR we call, common mode rejection ratio is very high in this balanced transmission. This is called RS485. Carefully see here, there is a termination wire. You can connect 32 devices in one bus, 2 wire you take it. You go on looping it to all the devices. How many you can go? Today you have up to 256 also you can go. So before it used to be standard, it was only 32. So this is very practical, you see here. This and CAN bus we are going to talk afterwards has a lot of similarities. They're exactly similar exactly. Okay. Now this is a termination resistor you have to put at the end of one device. So you got 20, 30 devices. This is excellent. Lot of instrumentation sensors you are getting in RS485, so you can use that. Now there are a lot of comparison of RS485. I'm not going to go through this slide completely. The distance of RS485 I have used personally up to 4 kilometers. Okay, 4 kilometers. There is no data loss, nothing you can get. You can go up to 1 Mbps for 1 kilometer distance speed. So good for agricultural purpose use. They are also used heavily on an industry sector also. So you consider using RS485 2 wire system in anywhere you want to use. Or I told them 4 to 20 milliampere also good one. We come back to Ethernet to understand very short. What is Ethernet? We all know Ethernet, 10 Mbps, 100 Mbps, whatever it is there. See, Ethernet has used in transformer for isolation, so you cannot short. So very good if you have, let's say, poly house or anywhere else enclosed environment, you can use Ethernet. There's no problem at all. But Ethernet is slightly expensive technique than other ones. Very high speed data can go. They are isolated by transformers. We already studied what is a transformer. There is no shorting will come. And they also use the same twisted pair wire. 2 wires are twisted, so the noise will become same. And the advantage is it has got a collision detection also. We'll come back to collision detection. I am talking, Indramani is talking now. Both are simultaneously talking, there will be collision in this line. How to do it? There are techniques available. Ethernet is the first one started the collision detection. Our CAN bus has also collision detection. So, but RS485 doesn't have collision detection. RS485 only one unidirectional you can use it. That means master slave, half duplex what they call. When I talk, Indramani cannot talk. We both cannot talk. If I talk, data will get corrupted. Whereas in the CAN bus, he will not talk unless he listens first. We'll come back to that. So, sorry. In this, one more thing you have to remember: wherever you use the Ethernet, you can have the power on Ethernet. Power also can go through limited power for sensors, whatever it is. You can same through same wire power. Also, you can carry the same wire. No need to have another power supply to take it. Let me put that somewhere about half ampere, small one, like a charging, less than charging a cell phone for power, much less than that. For sensors, it's enough. Then we come to CAN network, controller area network. This is there is a standard for CAN network. Our automobiles also have CAN network now. CAN they have, like OBD2 is a standard for automobiles. In this, I will try today. If not, tomorrow will come. We will try to explain the J1939 simply for you to understand what all features you will get from a tractor. Okay. This I have already done for a Brazil company. So I will explain you that what it comes out. So this is CAN is used. Is J1939 is common for heavy trucks, buses, and tractors. All these things is the CAN product. CAN also you see 2 wires, CAN high and low, and there are termination like RS4 is fine. Okay. Now when you look for CAN bus, they work at 1000 kbps or 500 kbps, but J1939 is 250 kbps speed only. That is a standard given. Now CAN there are multiple CAN wires can come. One can control the engine side and full tractor. Another one go for implement side. So this is a messaging system actually. CAN is a messaging system. Everybody will start telling a message. The temperature sensor will tell a message. Everybody will be listening actually. Whoever has a priority his message will go through. For example, we both are now, Dr. Indramani want to talk with me now. He will wait for a time I stop talking, then he will talk. But the moment he knows I'm talking, he will not interrupt me. That is the idea. If you try to interrupt, my voice will overpower him in CAN bus. So that's the advantage. If somebody tries to call, he will overpower that fellow for a certain period, not full length. So the moment he started, then he realizes, okay, he's talking here, let him talk. So that is how the CAN bus works. It's very important for agriculture implements. We have to do it because we are behind 25 years at least. Okay. Now this is a comparison. You can find the comparison of the all the buses what we discussed. The local buses of SPI, I2C. I think we heard at least 30-40 times. I think we should at least click in the mind a little bit. URT today we learned, and LIN bus we learned today a little bit. What is the application? Single wire can go to all the motors. For example, starting a motor, stopping a motor. Simple application you can use a LIN bus. CAN bus is a very heavily data exchange messaging system actually. These are all the possible distance to be used. Next one I'll cover RFID, where I actually made a living with RFID for almost 15 years. Now we are not much into RFID, but RFID is a very interesting area which we use in agriculture. Very first we used in agriculture probably 35, 40 years back. More than 40 years we are using agriculture RFID. RFID, all of you opening the room one, they come as labels. You can put processing everywhere labels. You can identify things at a particular distance. I'll show you some of the example what we are using. Very first RFID came 40 years back was cow feeding in Europe, especially they used for milking when it goes. The shutter, whatever is there for the cow, will close it if it has spent, let us say, half an hour feeding. Water also they can. So they put a tag there which are 125 kilohertz frequency. This is not really RFID 125 kilohertz, but let's assume that. So they are the ones which are used to access card today in all the corporate everywhere. You go there, show your card. So the next one is available in RFID is what you call the high frequency. This is the low frequency first one. Second one is 13.56 megahertz, which are all the MyFair cards which are used to be, where you pay through credit card. Now you tap it, 2000 rupees, it will debit automatically. That is using this technology. Okay. You can read and write on the card. This was very useful in agriculture. Conveyor belt everywhere when you see it, very useful. But the distance is only about 10. Maximum you can go up to 50 centimeters with this. Third one is UHF card. Third one is ultra high frequency cards, which are used toll booth nowadays in the car. You go and charge whatever is started right now is existing for warehousing, identification, so many things it's being used. You also have active card you can carry with you, or you can put on a cow or whatever it is to identify where the movement of things. They are also used active We will not go so detailed into it. Only I want to introduce the concept, and you people will pick up. That is, otherwise time is very short. We have to continue. We'll come back to Bluetooth now. So Bluetooth is something like a Wi-Fi only. We'll come back to Wi-Fi. We'll not come to Wi-Fi. See, Bluetooth and BLE. Latest one is Bluetooth low energy. We are talking about, and what we have, that is Bluetooth 5.0 and 4.0. They are talking now. Your latest cell phones have. They are low energy. They can only transmit less data. But today in a cell phone, you have got both technology. You have normal standard Bluetooth as well as BLE technology. It decides on which one to use. Bluetooth can go very high speeds. BLE can go less data rate, very ideal for cow detection or any of the ideas you want. But distance is practically it works only for 20-30 meters. But people claim, for example, I will show you some slides. They claim up to 800 meters. But again, the cost-benefit ratio when you see, you want to use it 20-30 meters, 10 meters, 20 meters distance, use the BLE. Very cheap. They're hardly few dollars is inside. They got a lot of features in the BLE when you go. See, Bluetooth has got audio application. Okay, BLE has got a data, and it can beacon services. So suppose we 5 of them carrying in, each one will know who is the fellow nearby, how much distance it is. Data can transfer from each one. It makes a network. You can make a mesh network. And so that is the advantage of BLE. It's not very difficult to do it. Most of the libraries available, like I told you, it's not very difficult. So this is a BLE. Next one. We'll go next one. ISM band we have. ISM band is very interesting. That is, I told you, industrial, scientific, and medical band. You see, when you look at radio frequency spectrum, more than 50% are defense reserved. We cannot use it. And we only hear about 2G scam and 3G scam or 4G scam. We hear only that word. But we have to understand the radio spectrum and why they are fighting for the radio spectrum. So we will not go into detail. We'll see that also a little bit, but we'll not go to that problem now. And this is excellent to use for up to, you have 20-30 meters. You want to transfer some data with low power. You need a battery, but not ultra low power. But it can do for you for 15 days, 1 month. 15 days you can do, 1 week battery will work, normal batteries. There you can use this. The Nordic is one. Many companies are there. I don't want to promote any company here. It's a very popular one. This hardly about price wise. If you see, probably 40 rupees to 60 rupees is the device, which works. This all works. This, for example, this works in 2.4 gigahertz range. See, BLE Bluetooth is also works on 2.4 gigahertz. This ISM band also 2.4 gigahertz. Your Wi-Fi also 2.4 gigahertz. See, Wi-Fi is a continuously different channel. I think when you use Wi-Fi, you know, 2.4 means you assume that there are 10 channels you divide it between 2.3 to 2.4. So you have 2.31 to 3.2, 2.32 to 3.3, like that it is there. But these Bluetooth and these guys, they half the frequency, find out which is free and use it. Let's not go into details about that right now. But it's an option for you to use. Proprietary, you have your own network with a low-cost solution. So these are frequency bands. When you use it, you must remember in this very carefully. India uses 865, 868 megahertz. That's allowed. And 433 is not allowed in India. Even though we have drones today, all using 433. I think many of the drones from China are coming out 433 because US is 433 megahertz. US uses 900 megahertz. But 865 is Europe and India. You have to be careful. Probably anytime the resolution will change it because it's all defense controlled also. They will allow 433 for small toys and stuff like that. But I think 860 is also available in drones. So when you procure, you carefully look at it, the frequency spectrum. You've got different type of topology you can make networking. You have mesh topology, ring topology, star topology. This all I will not explain you. Your sensors are different places, far away. Suppose like yesterday, this was yesterday, 100, 200 diameter goes. You want to have another one, very long distance. You have to one more device in between. It will take the data from here and go half link. So you can link any amount of data when you want to go for mesh network. So you have the option of doing on the field. You have Zigbee, what they call Zigbee is similar to the protocol. They are also available in 2.4 gigahertz and 950. It's a heavily loaded stack. Protocol we'll learn that time. We'll know Zigbee. So don't worry about Zigbee right now. It's also one of the stack. We'll learn stack afterwards. We'll come back. And now connectivity, when you see BLE, Wi-Fi, Zigbee, Zigbee is used. It was used heavily before several years, but I would suggest BLE and Wi-Fi are much cheaper option for you than much cheaper. Wi-Fi is $1 or something. BLE is slightly expensive, $2, $2.5. You'll get a solution. We come back to the next one. Very important topic is we have a LoRa, Zigbee, Bluetooth. We learned everything. We'll come back to an LTE, the long-term evolution. LTE, what we have, volt technology. LoRa is the one thing what I think I will talk for a few minutes now, 3-4 minutes. LoRa is the one what I see the future probably come. This is what you call is the spread spectrum technology. Okay. In short, I don't want to confuse you. You can transmit up to 3 kilometers, but only few bytes, 20, 30 bytes in a second, in 2 seconds, 3 seconds. Okay. You need one receiver. You can go up to several kilometers. Okay. Several kilometers. And you can connect many, many devices. See, in a farm, you see, I have got a water well, everything. It can get through the center of the village. And from there, you need some other transmission to get out, Wi-Fi or whatever it is, we see that. So LoRa has a future. I've written some articles on LoRa, how it can be used. People are trying in agriculture outside. But I think LoRa, one thing is you need every village a receiver. A receiver, I mean, they collect the data everywhere. And then it goes to Wi-Fi on the broadband out. But LoRa can be used for low data rate only, not for cameras, not for all those things. So IoT, when you look at IoT, real IoT, LoRa is one. It's because you don't pay any money for it. You don't pay any money for it, it's free. So if you have 100, 200 farmers are using it, with one SIM card, your job will be done. Okay. So this is one thing we have to seriously look at it.
Sir, your mic is muted, I think.
You're not audible, Dr. Syed.
Your mic got muted. Sir, unmute your mic.
I'm sorry, somewhere clicking it went off. I'm very sorry. So class A you have, class A is the one which is battery powered, we have applications, and class C fully powered we have. Then LoRa, only what you have to concentrate is where you'll collect the data and send it back. See, there are limitations in LoRa. You can listen at a time only to 128 sensors at a time, what I'm talking. So, and you don't require data every second to come from most agricultural applications. I think this could be a solution given by, we can make an initiative to make it certain villages to put, and at least sensors, water level. For example, even you will understand whether road roller is going or not. Okay, because you don't require data very often. You don't require each sensor to give every 5 seconds, 10 seconds data sense. It's enough for us in most of the applications, excepting of course high technology. What we come to big data, that is altogether different. For that we require a different solution. Normal farm management and data collection, this will be one of the solutions probably ideal for India. Now we come to the second one is LTE, which we are using as 4G. For example, today we are talking 4G solution, and the narrowband IoT, NB-IoT they call. Okay, this is IoT they try to make. India is not available till now. For last 1.5 years we are trying to find out. Nobody hosts NB-IoT till now. Okay, their trial available from Geo. Everybody can test it. They ask us to use, instead of 4G, use NB-IoT because price is really different, but it's no decision being done. They are trying actually for metering solutions. Okay, you have one big area in metering solutions. All the meters, what you have, water meters, there, electricity meters, it's a huge number. In agriculture, or similar case, but meters are all in cities and all there. One location it is, whereas agriculture is far away. So we have to think about a solution. LTE has got different advantage. Of course, very high data rate you can go. In LTE, you have also different versions. You have Cat 1, Cat 0. I don't know whether I have a slide. I'll see. No, I don't have it. So there is Cat 0, Cat 1 we have. That means how many Mbps you can transfer data. So some of them without voice, you can transfer only that. So 4G modules are now cheap, affordable. Just before the lockdown, I got the price somewhere about much less than 1,000 rupees. So which was used to be 3,000-4,000 rupees a module for 4G. Otherwise, we are using till now 2G only, all GSM modules. So you have LAN, LPWAN, there's a LoRa, and the cellular. So LAN is short distance, LoRa is long distance, and cellular is also long distance. So there are different parameters you can compare, but I think I gave you a hint. You can go and read about this. And there are a lot of parameters comes in wireless when you see. This is very important for an agriculture engineer to read about it, because as a decision maker, you must know what are the possibilities. You can't call an electronic guy and decide what you have, because everybody is a businessman. Like Sigbox is a company which is giving its own solution on the same what we call is the like LoRa technology, is spread spectrum. What do you call? They use 2.4 gigahertz, for example, to send data of something like 100 hertz data. Okay, that's spread spectrum. This is excellent technology. Now there is no interference there. It can actually spread spectrum. This LoRa technology can go up to 25 kilometers if you have line of sight. Okay. What I'm telling is, in building, in farm and all, you can expect easily to go for a couple of kilometers. I think 5 kilometers that it is really possible farm. In cities, it's 1 or 2 kilometers. I have tested myself at least about 1 or 2 kilometers. Now we come back to the different advantage you will see on this. Now I come back to the next one, satellite, this one. So there are applications in agriculture also, satellite, like weather stations. You have remote weather stations. You can use, there are satellites which are going continuously moving around. There are different type of satellites. So satellites can pick up data from you. You cannot pick up continuously. They can also pick up the data only few bytes. Now, that few bytes of data satellites moves, it picks up from different places and sent to stations automatically. You are getting through your internet. The information, just an email you will get. Okay. This particular one, weather station, this is a project from Brazil. I got it before a couple of years. So they got a weather station details they given, and they want to fit in a tractor. This is a board we designed for the tractor, which gives Arbocom OG2. Arbocom is one of the company which gives satellites. Iridium, you know, Immersat, the gun type, all can be used. And here is the different features are available. But to tell you short, this is not a big deal. It's not some very high technology. No, these modules, what you see here, they are available already. You have to understand the protocol, how it is used. You have to be careful in PCB design, noise will not come. And you have to be careful about your protocols, what you're using. That's all. I think with this, I will stop now. We will continue tomorrow. The protocols will go. I think it should be correct time. Now we can stop this topic, and we will go for some questions, quick questions we have. We can go for it.
Yeah.
Anybody in the panel, anybody want to raise their hand?
I have a small question.
Please.
So you talked about RS. Can you hear me?
Yeah, sure.
Okay. You talked about RS-485 communication. So I wanted to know whether it's has any more advantages than RS-232 communication, because we use RS-232 all the time.
No, RS-232 you can't use it for long distance. RS-232 is good for a table for computer connection, 1 or 2 meters. If you go more than 5 meters, it will be a problem. So RS-485, you can go very long distances. Okay. And noise, like I told, noise will not be there.
Okay, thank you.
Okay. Anybody can tell also what you want to learn from this. Now I have got somebody, Mahendra Kumar Mohanty. Can you enable him, please? From the attendees,
can you transfer the host?
Oh, I'm sorry. Host is with me. Yes, done. Sorry about that. Okay. Mahendra Kumar Mohanty, can you talk please now? You have to enable your mic, unmute your mic and talk. We have Again, we have Gauripati Rao. A question, please ask him.
Yeah. Hello, sir. Yeah.
Yeah.
Good evening, sir. I need to ask some 3-4 basic questions, sir. Why there is a cost variation in GPS price? Actually, I was searching through some research papers, and I found that some GPS were coming around 10,000 rupees, and some were coming around 2
No,
lakh.
no, no. I would suggest you come to the point because the time is very short.
Yeah, that only, sir. I need to know why there is variation. Anything particular about that
No,
specification?
you're not searched enough about it. You're not used it. We are using for 20 years GPS. So
Yeah.
we buy normally in volumes of 500,000. So this is the price. One, two pieces will be around 2,000-3,000 only. You specifically, you can contact me for this separately. You can contact us. No problem at all.
Then second, sir, circular error probability, sir. Can you tell me about that? What is this circular error probability? That is around 50%.
No. CEP. I told you the CEP is they can because this is actually you are trying to find out from the timings the location. So 50% only is guaranteed by the guy who wrote the software firmware. Okay. So which means you take 100 points you are getting from the 50 guarantees less than 2.5. Normally it is 1 meter, 0.5 meters normally. Okay. But more than 50% is maybe some of them are 3%, some of them 3 meters, some of 3.5 meters. Okay.
Okay, sir. And sir, last question. One more question, sir. Last question. Hello.
Yeah, please go ahead.
Yeah, sir. Yesterday you spoke about sensor flow in turbine machines, sir. What some algorithms you have mentioned? Can you tell me, sir, what type of algorithm?
That is we'll have it. No, you have to make your own. We'll talk it separately on that because I told you starting and stopping turbines will give problem. Okay. That this discussion because others all interest is different, so we'll take care of everybody's interest. Thank you for your question. Now, Mahindra, you're there to talk now. Okay. Somebody else is. I think nothing is there. I think according to me, nobody else is there. So, Dr. Indramani, you take it over.
Thank you. Thank you, Dr. Syed. It was a very good session on connectivity. Now, as time is short and we have two speakers, so we will go immediately to Dr. Sangeeta Chopra. She is our colleague at IRI in the Division of Agricultural Engineering, Principal Scientist. She did her BTech from IIT Roorkee and Masters from IIT Kharagpur in Machine, Drives and Power Electronics, and her PhD from PAU Ludhiana in Energy Science and Technology. She is a Fulbright Nehru Academic Professional Excellence Fellow and has two important projects from USAID. We are working on this area, this solar refrigerator, gridless, batteryless, automated. So this is again end-to-end solution, developing it and taking it to the farmer's field, installing it and showing it its capability. Sangeeta will cover the technology and also how we are doing at farmer's field, and from here only up to today's data, she will tell that how you can control from sitting in your office or home here and see the performance of the system. Dr. Sangeeta, please be brief and cover in a given time. So we will be finishing all these things by 7:15 or so.
Okay, thank you. Good evening, everyone. So the screen, will you be playing the presentation or should I share the screen?
Now it is from here.
You tell next is faster if you tell next.
Should I share the screen?
Next.
Ma'am, you just need to say next. I'll change it.
Yeah. If so, I can't see my presentation yet. Is the present? I cannot see the presentation.
It is there. Everybody visible. It's visible to me.
Oh, yeah. Okay. 1 minute, sir. It's not visible to me only.
So you can see on your laptop.
1 minute, sir. I can't see.
You can see my face. You can see my face.
Yes. Give me a minute, sir. I can't see the presentation right now. Okay, yes, I can see it. Sorry. So good evening, everyone. I'm here to talk about, as Dr. Indramani has stated, it's automated solar refrigerated evaporatively cooled storage structures for smallholder farmers. And we have worked on this with scientists from Michigan State University, Dr. Randolph Baudry, he is in Department of Horticulture, and Dr. Norbert Mueller in the Department of Mechanical Engineering. And we've been funded by 2 grants from USAID. Next, please. Next, sir. Okay. So initially, I wanted to talk about what's about these solar refrigerated structures, the principle behind it. So we have a combination of evaporative cooling and solar refrigeration in this system. So the initial step is evaporative cooling. The walls are wet, and as a result, the temperatures, there's a modest reduction. And then we've added solar refrigeration. So if you see figure 1, you can see the evaporatively cooled wall, the schematic, and there is the insulation with high R value material so that we can add refrigeration too. And if you see the second figure, there is the solar panels for solar refrigeration, and the inverter is gridless and batteryless. So neither do we have the grid nor the batteries. And the refrigeration system is specially designed. So the evaporator coil is split into 2. One cools the air and the other cools the water. The water is in a drum, so that's the thermal storage. And that cold water keeps the room cool at night. So we have thermal storage, which is a water battery for nighttime cooling. And along with this, we have added Pyranometer for solar insolation sensing. So what happens is when there is less sunlight, we control the compressor so that it takes less current. And if the sunlight increases, the compressor is able to take more current. If there's a cloud, the compressor shuts down temporarily. So this is what we've tried to do. And on the right figure, you can see we have 14 solar panels, and 7 of them are in series. So there are 2 strings. Each panel is around 350 watts. Next, please. So we have, from ancient times, evaporative cool structures are being used. I have also worked on this in CIFET, and many other scientists have been working on evaporative cooled structures. So the first figure you see is the traditional evaporatively cooled structure. That's the brick sand brick, where the sand is wetted and the water evaporates and keeps the room cool. Now we tried to see if there were any other alternate wall designs which could be possible, which could be maybe give us better results than a brick sand brick. And if you see the second structure, second figure here, that's mathematical modeling. And the BSB stands for the brick sand brick. So if we start in this figure, if we start from the BSB, that has a huge thermal mass and very low thermal transmittance. So the y-axis, you can see the change in temperature of the product is very little, just around 2 degrees. And if you go to the right-hand top, the MSF, that is the mesh supported fabric, which has high thermal transmittance and a very low thermal mass. As a result, the temperature change that can happen in the product is much more, like 4 times that of the brick sand brick. So from our mathematical modeling suggested that we could have some more wall designs which could give better results just for evaporative cooling. As you can see, there's pervious concrete, which is somehow midway. So if you see the last figure, we have the mesh. Instead of the brick sand brick, we can also have alternatively a mesh supported fabric wall on the left side, as you can see the drawing, or a pervious concrete wall. So different wall designs for evaporative cooling are possible. Next, please. So our study continued in IERI, and these 3 figures that you can see here are 100 kg structures. So we made 100 kg of each wall design. As you can see, the first one is mesh and fabric. So it's simple to make. The fabric is wetted, and there's a mesh inside of that. The second one is the traditional one, brick sand brick. And the third one is the pervious concrete. So if you see the graph below, the black line shows the ambient temperatures day and night, which is like in the day it goes around 40 degrees Celsius. And the green line, and so all of them start at time 0. Time is the x-axis. All of them start from 40 Celsius. And as the product comes down, you can see the temperature of the product for mesh supported fabric is the lowest. So that gave us the best results. As a result, we thought we would work with the mesh supported fabric evaporative cool structure. Next, please. So here you can see the mesh supported fabric 2-ton structure, which we built in IAR, right? And it gives modest temperature reductions. So if you see the right side figures up top, the red line is the ambient temperature and the inside is around 30 Celsius when the outside is 40. So around 10 degrees reduction, and the humidity is 80%. So we all know this. Next, please. So that was our basis for the evaporative cool structure. And then we started adding to see what was possible, what all is possible to make it solar refrigeration. So we have done a lot of research in these so many days. And on the left-hand side, you can see that we have this evaporative cool structure with this special fabric. The fabric that we have here has been tested at Michigan State. So they tested around 100 fabrics and came up with the best one, which could spread water through the fabric and not let it just fall down or something. And you can see the lower diagram shows all the number of panels that we have used here. And the right side diagram shows that how the energy from the panels was converted to the energy which could be given to the refrigeration system, which is on the top right-hand side. So there were several systems that we used from all over the world, actually. You can see we have a MPP Solar, we have SMA US, we have SMA India, and we have a Cyber inverter. So we checked all over and we found that there were only so many systems which could work without grid and without batteries. I mean, there are only a few in number. That is called like a secure power supply. So only those kind of systems. Otherwise, the on-grid ones, mostly the inverters that are available are the on-grid, for which if there's no grid, it will not give power. Or else they are off-grid, which means they need batteries. So we looked for systems which do not need the grid and which do not need batteries, and we were successful. And we tried all of these with our system in IARI. Next, please. This is a specially designed refrigeration system. So the evaporator coil has been split into two for cooling the air and cooling water in the drum. And on the right side, you can see the water battery. So the water from the drum, the cold water is pumped into this battery up top, the reservoir of water. And the pump is also run from the solar energy. And the motor, which is to wash the panels, is also run from the same solar energy. Next, please. So here you see that these are some extra features that we've added, which as I was telling you, to make the system automatic. That is, if there is less solar insolation, then it should run on a lower, take less current. And if there's more solar insolation, the compressor should take more current. So you can see in the lower left-hand side, we have this Pyranometer for solar sensing. And then those small panels that you can see up top are used for running that microcontroller that we are running for the control. And this middle figure, we are taking out the indoor PCB because we are putting in our own signal there. And the last one you can see is the unit that is standing outside the refrigeration system, which is run from the panels and which is giving that, that change into the indoor unit. So you see the pyranometers, as it's written here, pyranometers or solar panels are for sensing the sunlight insolation. The amount of sunlight changes the amount. So according to the amount of sunlight, we have used the microcontroller and we change the amount of resistance across the PCB of the inner unit. So that changes the compressor demand, how much the compressor is going to demand. So this is working successfully. Next, please. So as you can see, like this is on a particular typical day. So around 8 to 9, when there's less sunlight, the refrigeration system draws 3 to 3.5 amperes. Then when it goes a bit high, like higher intensity, 7.5 to 8 amperes, and goes down again in the evening. And then in the night, it just turns off because there's no solar energy. And if there is a cloud cover, then we are activating the relay and it stops the power temporarily. And as soon as the cloud cover goes away, the system starts again. So it's working automatically nowadays. Next, please. As you can see here this is just a control panel that we have fitted with the system with our refrigeration structure. So you can see on the left side, we have the solar panel currents. So the two strings are giving two set of currents. So that's voltage up top, then the current, and then another voltage and current from the flat panels and the west panels. I mean, we did have direction in the panels also. And on the right-hand side, you can see that the grid current is 0 almost. So we draw no grid current. This grid current 0.95 amperes is for running these meters actually. Next, please. So we are, presently we have got a grant funding from peer Cycle 7 program from National Academies of Sciences, Engineering and Medicine in Washington, DC. And we are going to make 3 of these structures in 3 states of India, that is Rajasthan, Haryana, and Delhi. And the one in Rajasthan in village Picholia and Ajmer is completed and is running. Even though we are in our houses, the system is running, is being used by the farmers, which makes me very happy about it. We started it in March of this year. And it's being run, our partners are Krishak Vikas Sansthan and an FPO there. In Haryana, we have, as you can see below, we have gone and selected the site. It's Chamrara. The work has started, but has stopped because of this COVID lockdown. And it's in Panipat. And Delhi, we still have to identify, but that's our job that we have to do. Next, please. This is the farm sunfrit. We also call it the farm sunfrit, the solar refrigerated evaporatively cooled structure. We've named it farm sunfrit, and you can see this is how it looks in village Picholia. Next. So you can see on a typical, this is for a few days. The outside temperature is by the ambient red line. It shows around 40 up to 40 Celsius. And the inside temperature is average around 9.59 degrees. That's the green line, the green. And so when during the daytime, the temperature goes low. And as the solar energy stops, only it's just the water battery which is cooling, the temperature starts rising until the next day comes and the temperature goes down again. And the blue line is for the drum, the temperature in the water, the temperature of the water in the drum. So you see it's going near 0. If we don't pump that water, the water freezes. Next, please. So in Rajasthan, in Haryana, we've also set up this in Rajasthan, in Picholia village, we've also set up this remote instrumentation. And this is by Hobo. It is a company in the United States called Onset. And we set this up for taking environment data as well as all the currents and voltages. And this is how it looks there. And you can see the link below. So this is a live link. After the presentation is over, if you click on this link, it'll show the dashboard for just now and the past week. And you can also see the past month data. So this data is being taken every 30 minutes and is being uploaded on the cloud every 6 hours. So even sitting here during lockdown, I'm able, my colleagues in Michigan State, who are also listening in actually, and myself, we can see the data at any time. Next, please. Along with doing all this work, we are also training. The system is not difficult to make. We are training the farmers. It is being made by a team who we have trained at IARI, and they're also training the farmers. So it's built on columns, and it's got simple low-cost insulation like 2-inch thermocol styrofoam panels. You can see that. And we have the third figure up top you see is for hanging the water battery. And in the lower right figure, you can see Dr. Randolph Botry there training the person how to use the autoclaved aerated concrete blocks. So we've not used bricks anywhere. All these columns that you see are from it's called AAC blocks. They're commercially available by CK Birla Group and all. And the thermal conductivity of these AAC blocks is 1/8 of that of bricks. So we've not used bricks, we've used these because they are really good insulators. Next. We have used Amaranth for storing, we've stored many things here as for testing, for evaluating the structure. In Delhi, in IRI, we've stored tomatoes, amaranth, and some other fruits and vegetables. But here, the idea here, I'm trying to propose that amaranth can be used as a model crop for testing the storage. It's not that we are using the storage to test the amaranth. We are using the amaranth to test the storage, the performance of the storage structure. So as you can see, the amaranth, it's very easy. It's the senescence parameters of amaranth, which change with storage temperature and humidity as the amaranth respires. These parameters are very easily measurable. Like you can see, we can count the leaf yellowing. We can count how many leaves have fallen off. We can see how much wilting is there. So these are easily measurable parameters, and they do not require very sophisticated instrumentation. So we are doing this experiment that we are storing amaranth in all these storages, and we are trying to see if amaranth can be used as the model to test the storage itself. So as you can see up top on the right-hand side, you can see on the 0th day, this is how it looks. But on the 4th day, just for an example, a typical 4th day, you can see how many leaves have the abscission, how many abscission and EC structure in the ordinary room. It's like a lot of leaves have fallen off, whereas in the SREC, the solar refrigerator structure, and also the refrigerator, they don't fall off. So we've done some 1,000 or 2,000 samples already. We have some students working on this, and we are near to submission of a manuscript on this. And as you can see, the graph below shows the yellowing. So in the refrigerated structure and the refrigerator, the lines are absolutely near 0%. So there's no yellowing over 8 days, whereas the yellow leaves are around 50 or 60% or 70% in the ordinary evaporative cold room and the ordinary uncooled room that was our control. Next, please. Next. Okay, so this is the current situation that we have here as on April 27, 2020. You can see that our structure in Pecholia has 814 kgs of tomatoes and 8,000 eggs. So even, especially during the lockdown period, the farmers are unable to sell their produce because the mandis have collapsed. So they are able to put these, their produce in this structure at Pecholia. And some people have told me that in Haryana and Delhi also that they wish that they had these structures. And so the farm at Pecholia has no electrical connection. They don't have it also to use. So now the farmers are amazed because they can see a structure which, even in spite of no electricity, they're having a cold room. And there's no batteries, there's nothing to take care of or to maintain a lot. And the cloth that you can see is wetted. And so you can see that from March, we started from March, we inaugurated it. And so the 1, 2, 3, 5th line, you can see there are 5,250 eggs for 27 days. So from 1st of April, he's kept the eggs till today. So this was made in a hurry, but the star marks are for the produce, which is lying even today in the structure. So, but what makes me happy and what makes our colleagues happy is even when I am unable to travel, I'm unable to go to Pecholia to do anything there. I want to make some changes, but the structure operates every day. So every day there is sun, and every day it gets cold, and every day I can see the data in that the dashboard, and so there is cooling, and the farmers, in spite of lockdown, it's in the village itself, the farmers are able to keep their produce. And they are not only that, they're keeping tomatoes, and they're making tomato puree out of it, then they're keeping the puree inside, and so they are also taking out the eggs, and they're putting the eggs back in. So that's what's happening as of now. Next, please. Well, Thank you so much.
Thank you. Is her line broke or she's completed?
I'm here.
Yeah, please. It's over? You completed?
Yes, from my side.
Thank you. I'll take some questions. Yeah, thank you very much, Doctor. There are some questions. I will take questions.
Sure.
And there is one from Dr. Uday Kodke, that is from Parbani. He's asking question, what is the cost of such a structure? There's another question regarding whether you're using sun tracking technique in this or not. You're tracking the sun or not. These two questions you can answer, please.
Yeah, the cost is around 5 lakh rupees. I mean, yeah, approximately.
Are you tracking the sun for the solar panel or
no?
Is it
No, we are not.
Okay, then. Another question is
panels. We have to track 14. I mean, there are 14 panels, so we yet have to think of a way how to do that. I'm sure we can do it, but that's still part of our research, maybe.
Okay. Another question from Samir Kulkarni is asking basically whether its capacity is 100 kg. So whether you do it as a cooperative or is it individual farmers are having this?
It's a cooperative, sir. The structure is in Pecholia. This, not the 100 kg, this is 2-ton structure. It's in Pecholia, and many farmers in that farming community are able to come and use the structure. 100 kg we've not built anywhere. It's just in IERI. But people can build it.
Okay, thank you. Mahesh, question 5 lakhs, I think it's 100 kg capacity. Am I right?
No, 2 tons.
2 tons. Okay, fine. Another question is that how about gas production and respiration heat generation control? I don't understand this.
So the respiration heat, yes, does get generated, but the temperatures are low. So accordingly, the respiration heat is less. I mean, the inside temperatures, if there is time, I don't know if there's any more time, but if you go on that slide and if you link that dashboard link there, everyone can see the data right now. So the inside temperatures go down to, I mean, I'm particularly very happy when they go down to 8, 9, 10. And yesterday they loaded the structure, so sometimes it goes up high. So my colleagues at Michigan State, I mean, he's listening, but they tell me in the morning, hey, something happened in your structure today. So we know every day what's happening, even in spite of not going there.
Okay, I have 2 questions. Thank you. I have 2 questions. I will ask for C.R. Mehta. Dr. C.R. Mehta, you have a question? You can go ahead, please.
Yeah, madam, I have one question.
Yes,
you have put one plant in Rajasthan. So what is the peak power of that plant?
5 kilowatts, sir.
5 kilowatt. Okay. So will you be able to store 2 ton in that?
So right now we have 800 kgs and 8,000 eggs.
Mm-hmm.
So the structure size is to maintain 2 tons.
Okay. Thank you. Sorry. Go ahead.
I want to say that we have tested this entire system at IERI. The proof of concept is tested there, and we used lights to simulate produce for heat.
Thank you. Another question, Dr. Narendra Shah, please.
Yeah, so I was just wondering if you can have 2 sort of compartments in the structure so that there are some commodities which are happily stored between 10 to 15 degrees Celsius. And so you don't really need to go to 0 degrees Celsius. And in the same structure, is it possible to sort of have 2 compartments at the same time?
So surely that is possible, but I would like to say here is that the inside temperature is anywhere around 10 only. We don't allow it to go to 0 but the drum water goes down to 0. That which is getting pumped in the water battery, the reservoir is near about 0 and then gets hot as the night comes. But the inside temperature, the air temperature is around 8 to 10 Celsius. But surely we can have compartments. I mean, we can have shelves, we can have compartments provided the air blows, airflow.
Thank you. Mr. Sahu, your mic, enable your mic and please speak. Ask your question.
Sir, installations in our state, to whom should I contact?
I didn't understand the question.
No, whom to contact if you want to get details? You contact ASAE, they will forward the
All of us.
details to the customer.
Okay, thank you, sir. Thank you, sir. Thank you.
Dr. Gajendra Singh has a question. Sir has a question.
Yeah. Just one more just question, then I think Bhaskar. Yeah, just I'll come.
Dr. Gajendra Singh has a question.
Yeah, I'll come. I'll come. I'll give you last thing. Bhaskar, some questions.
Yes, sir.
Please.
Well, I joined in between. The question is the techno-economic feasibility across Indian sites where these systems finds its application, whether it has been done at your end, man, so that it could be given as a policy reform for the likely areas where this could be installed.
I would totally like it to be given as a policy reform somewhere. And yes, we've worked out the cost economics. We do not use electricity. There's no operating cost whatsoever of electricity. Even this guy who's washing the panels is using a motor which we are running from the solar panel itself. So you see, it works.
Yeah, it works. It's not a question, ma'am. But the question is.
Thank you.
Yeah.
No, wait. I think let the panelists, the speaker, let us speak first.
Dr. Yes, sir.
Okay. I think I will ask Dr. Gajendra Singh your question.
Well, congratulations, Sangeeta. Very good presentation. I have one thing to request. For a long term, can you do kind of a cost estimation of your system versus using only the solar panels for electricity generation and storing in batteries, keeping the prospects of the batteries life increasing and the capacity of batteries increasing? And what will be the long-term perspective?
I can do that, sir. I'll do that.
Okay. Yes.
Thank you. Yeah.
Thank you. I think now Dr. Indramani, please introduce the second speaker, please.
Thank you. Thank you so much, sir.
Thank you. Dr. Indramani.
Sir, it's mute.
It's okay now?
Now it's okay. Now it's okay.
Just I wanted to add that this is a very important project of IRI, and upscaling is next one, and this business model we have to develop, and our director and system is very much interested in this. What we are saying that you know that many parts of the country there's no electricity is available, and if we can ensure 1 week storage of this perishable produce, that can make a big change. So with this, we are working. Now, friends, next we have another very important speaker, Dr. Bora. So Dr. Ganesh Bora is Associate Professor of Precision Agriculture in the Department of Agriculture and Biological Engineering and Precision Agriculture Program Leader at Mississippi State University, USA. He did his BTech from Jabalpur, ME from AIT Bangkok, and then PhD from Kansas State University. He is a very accomplished scientist known world over in the area of precision agriculture, and he is going to speak on very important subject. And as I mentioned yesterday, since time is less, we had promised Dr. Syed that 7:20 will start. So let us start at 7:20. And now it is to Dr. Ganesh Bora, please.
Thank you, Dr. Indramani.
Thank you.
And I'll speak quite fast, and I can go as I teach students, I can go fast and slow depending on. So what I'll do is like kind of general things. I'll go first and we'll talk more interactive question answers than speaking from my side. Next. So I'll not go too much on precision ag. Most of you know what precision ag is. It has evolved from yield monitoring systems, then variable rate and chemical applications, sensors. All those things evolve based on what's needed by the agricultural system itself, and all the ways you see the information and data is quite important. That's what it's come to, like application, as we said, variable rate. That means like we are looking into optimizing resources with the right amount, right time, right place, right methods. And for all these things, we need data, information, process, and use it. And so for engineering perspective, again, precision ag is multidisciplinary. We need agronomist, horticulturist, climatologist, economist, but engineering point of view, which is very important to collect the data, make decisions, and how to use that. So that's what we are looking at in this presentation, that how to get information. Next. So again, with this, we're looking at information going into big data. That means we have lots of information, and from where those informations coming in and how to optimize those information for making decision. So mostly the engineer's job is to get information and make decisions. Next. So we have different sources coming in, at least right now, the field-based technologies and then drones coming in. All this together gets very huge amount of data. It takes time. The challenges are very, very important, not only acquiring the data, transfer the data, and use of those data by processing. So it takes time, and how to use it, that's one of the things. Next. So field sensors, many of you have used this one. This is a green seeker made by Oklahoma State University, and I had a chance to work with them. And it's basically getting NDVI, that's a greenness of the system, how it takes, like mounted on the tractor, so it can be on the go use for this information, but it's very costly. And the system, the sensor itself, like you have to put 20 to 30 sensors on the tractor, it's very costly again. So, but very good information. It has been used quite a bit. One sensor uses $3,000-4,000, and if you use 20 of them, you can make the math. Next. So with UAS or drones coming in, they have been tested, and it has been seen that the proof of concept has been done. The challenges are always there, the big drones, the small ones, and the helicopters, and mostly it is in the grain crops and also in animal husbandry with livestock. And we have moved from getting data to even applicators. Now aerial spraying is becoming quite popular in especially Southeast Asia. And we have done quite a bit of work in livestock, getting into the health of the cows, or how even looking into the physiology and the shape of the cow, you can basically estimate how much weight that can be for the beef market and or meat market or into the cattle industry. Next. And as I was saying, like we are looking into the volume, and the drone you see is a drone from Israel Defense Department, and this has been, they are done with defense, so they wanted to use in agriculture, and they send it to, when I was in North Dakota State, I was working with this drone, and this can go out of sight and using IC engines, no, not battery, so it can fly for a long time. And this type of drones has been now coming into agriculture sector to see how it can work. The point is, like, we have covering lots of information and from different sources and different aspects like yield, soil, seeds, moisture, waste, whatever you need, you're getting. And just see, if we fly a small drone for 30 minutes, we get about 60 gigabyte of data with just a simple 3 MB images. So that's just tip of the iceberg. So we need lots of information, lots of data, and the volume of data makes big data. If you talk to some of the other sectors like transport, health, they said, what big data do you get in agriculture? This is just simple information. Like if you fly the drones, you get 60 gigabyte of in 30 minutes. And how about getting the actual social data or yield data, seeds, moisture? So those adds up to a lots of data. And how do you use this is important. Next. As I was saying, the challenges were more the transfer. Do you need it immediately on the go, real time, or you need post-processing? The challenges with post-processing is like if you're using 1 year old data, the situation changes. If you're using at real time, means you are using the challenges of getting the data immediately to the tractor or the machine. So those are kind of challenges not only with infrastructure, but also manpower we need. And that's what we are looking into manpower development for using this along with the infrastructure. Next. So this is one of the available pictures. You can see agriculture system manager has become, basically this is one of the ag engineer job in US right now, that it's no more just only operating the tractor. It's a very heavy load on decision making. And this is just, this picture was taken about 2012. So you can see what's have evolved from since then. Next. Next. So data management was like, how do you manage the data on the go or from field sensors or UAS? We have done quite a bit work on field sensors. So what we are doing right now is those information compatible with UAS? Because UAS is very fast, cheap, and like kind of we can get the data right now. But only again, as you're saying, the field sensors we can get wired as well as wireless, but UAS has to be wireless. Otherwise, how can we use that? And again, to use that with applicators like system, how this data can be done. Next. So we are looking into this data link from the US to the machines and using small drones, and again, big drones, we can store the data and post-processing. I'll just show how we process the data immediately or at least kind of a day before or hour before. Next. So this is what our exact work we are working right now, that we acquire the data with the drone, and the data is stored either in the clouds or we store in the flash drive, and that web server can process the data, and that can be given to the users by internet, in mostly in iDevice, iPad, or iPhone on the farm. So you can upload the data where you are operating the tractor, get the data into the clouds, process it, and it takes about an hour or two, depending on what. So you get quite close to real time. Next. Next. So this is what exactly we are working in our field right now. And you can use this if you have, most of them have this connections, internet connections in the iPad and iPhone. So you can use this download those data immediately, get into your tractor, use the data for next. We are also using Wi-Fi right now to see and Bluetooth. So there are two technologies we are using on the go. One is 5G. There is a local cell phone provider, which is working with AT&T. They're giving us 5G on experimental basis. So how fast we can get the data immediately for the on-the-go application of chemicals. So that's the process we are using along with Wi-Fi. So if one goes off, the 5G comes in. So that's what, depending on how far the tractor is from the drone. Next. So we have developed algorithm based on, right now we are just using for corn nitrogen applications. And this is what just a algorithm pattern we are using, and based on what we need. Right now, as I said, for this our experiment, we are using only nitrogen for 3 applications. Next. Our overall strategy is to use this information. We have taken 3 years of data. So using these 3 years of data, if we can use AI and machine learning to get into our predictive application of nitrogen for this particular corn. Next. Next. So this pilot project we are using is in our university field. We have used green seeker and crop circle. Those are 2 field sensors to actually validate the data we get from UAS, so that we can kind of replace UAS, replace these field sensors by UAS. And we are using red and reddish green sensors from let me see the company. The center. Please, next. So we have 16 blocks. We applied to 3 different applications and 1 control. So to see what field sensors, and this is a direct map in Google Map, and we use 240 pounds per acre and 160, 80, and 1 control. So looking at what different informations we can get. Next. So in this project, we are looking at, especially during those who are familiar with corn, and different stages are based on the number of leaves they get. V6 is important, that's what it starts physiological growth. That means 6, and that's a very important, 6 leaves, that's a very important stage. So here the first application is done in initially during planting. The second side dressing is applied. The second application is in V6. They think like most of the development does. But recently they saw during flowering stage, that's the tasseling stage, whether they need fertilizer or not. If you fertilize, you might get excess increase in yield. That's what they're looking at from the agronomy side. So I'm collaborating with our soil fertility experts and agronomists to see if we can do that. And that has been kind of used if we need the third application during VT, that's V12 stage, that means flowering stage or tasseling stage. Next. So we took data in different stages by field sensors, and at the same time we are using the UAS to see how, and again, we are also using corn canopy and analysis by the agronomy. So we are doing it at the same time to see how we can use the US data instead of the field sensors. Next. So these are the fields, exact data taking. We are also using handheld as well as the two on that. I'll just see, so next. So this is my stand. I used two bicycles to make a stand to get the data on the field sensors for this. If you see on the back, that's the exact field we are using, and we are using center on the rotocopter and getting these two compared. If you can replace again the US data from the field sensors data. Next. Next. So this is again the data processing. We have to take out the soil data and get the georeference data so that we can go back and see what's going on the same area. We need that or not. And again, making a prescription map or even real time to gather the data, we need more georeference data. So we are using RTK GPS on this for corrections. Next. So we use the data for different application rates, and we saw quite a bit interesting part that field sensors, and they gave almost similar information, UAS, and within UAS, the red NDVI and red edge NDVI has quite distinctive. Next. So if you see the UAS red sensor, that NDVI, initially red edge and red did not have much difference, but when we go into that tassel stage, we get really different. So if you see, most of them are green, but it's the red one is more, there is a difference between zero, that's a control, and application. And in this case, we did not see much difference in different application rates. So those are the discussion point for agronomists, but for our engineering and data collection point of view, we saw clear, distinct images that we can use for application or not application. Next. There is the website we made for data processing. Actually, these are for farmers to use, and this right now is not working and it's down somehow, and I've been trying to work with our ITS guys and nobody's working right now, so that's another problem. And it would be up in 3-4 days. So what you can do, like upload the data immediately for the farmers. They don't need to talk to us. They fly the UAS, upload their data. They need definitely a password from the university, and they can get their own maps, prescription maps, use it, and whatever information they want to add it, they can add it in that map itself. So this is purely for farmers related, and they can use this on the go or post-processing immediately, and just if it comes up, maybe it will come up, you have the link, and if you see different dates, whatever date you use, we can get the data immediately and process it there. Next. Just validating the data we got. If you see the average NDVIs, for 0, it is 0.54. That was during V6, which is one important part for management decision. And if you see during Vita cell, it's like there's a distinct between 0 and the other application rate. But other application rates are not so much in difference. And that's how kind of making easy for that. Okay, you can go for 90 pounds per acre. So that's what the farmer or the decision-making process comes in. But there's a very distinct from application and non-application. Next. Just showing how this goes on with a graph. Next. So we found that definitely we can replace US and sensors. Those are because of easy to use, but the challenges would be how fast we can get the data, or how, if you want on the go, definitely still field sensors are very important. But if we can do it with near on the go or near real time, we still can use the US sensors, which are cheap and kind of very fast, and you get very good information and also easy to store and process. Next. Next. So I just wanted to take this opportunity to let you know that there are standards for applicators coming in, especially in Asia. It's being used right now for aerial applications. In US, still manned aircraft aerial application is quite important or very often used, but with aerial applications coming in by drones, it's not only cheaper, it's kind of very controlled. So that's how this standard might be quite important. And just to let you know that I represent the US committee on this ISO standard. So I had to get a vote for this. So USA has voted for this standard. It is still in draft. So I have the draft, and if anybody like for the ISC wants, I can share with you. Yeah. But this is still in draft, not has been approved by the ISO. Each country has approved, USA has approved with comments, and I'm sure India has also approved, because we haven't seen any dismissal by any other countries. So this is part 1, which is more environmental requirements. Part 2 is also coming. That's for more testings. And this is mostly used in China and Japan for paddy fields and orchards. Next. And this is again testing or evaluating the applicators, how you can done. This is I have taken directly from the ISO standard draft, just to show you that how the draft would come in. Next. So this is again using most of the agriculture machinery. ISO is represented by Technical Committee 23, which is on tractor and agriculture machinery. And this is directly in ASABE Machinery Committee 23. And the subcommittee is for crop protection is subcommittees 6, and the working group 25 is directly for unmanned aircraft system, which is working on this unmanned aerial spraying system. So there are 2 parts, as I said, and one is test methods, and another one is environmental requirement. Environmental requirement is almost done. We are supposed to go to Brazil in May for working, but this has been postponed, and we'll be having a Zoom meeting for that in May. And next would be test methods. I just wanted to next give some idea about ISO standards for UAS. Just to let you know that part 1 and part 2 has right now been suspended for upgrading, and it's not available, but you can get part 3 and part 4 on UAS, which is more operational procedures. Those are available, and also the civil engineering part is coming in as all this ISO 21895. Next. I just want to take this opportunity to let you know that we have done a project for precision agriculture in Bangladesh, India, Thailand, Vietnam. And as you know, I was I did my master's in Thailand. I still keep in contact with people at AIT, and Manjul has presented one, and we have worked together for 30 years, Manjul and me, and I've seen Piyush also here, and Manjul and Piyush took lead in Thailand, and the Bangladesh, Dr. Manjul Alam, we got a project, and when I was in North Dakota State, and Bangladesh, Thailand, India, Vietnam, there are 4 countries participated in that. We trained farmers and policymakers as well as scientists in those countries. And definitely Thailand was in Bangkok AIT, and in India it was Tezpur University. Some of you know Dr. Deven Barua, he was the country representative at that time. In Bangladesh, it was in Moimansingh, Bangladesh Agriculture Universities, and Vietnam, it was Hanoi Water Resource University. I've been to all these places to when the training was done, the workshop was done. I was personally working with them. And this pictures is from Bangladesh. And interestingly, I thought like, as I knew India and Thailand very well, and that the development would be more in India and Thailand, but I saw the involvement of all high level in Vietnam and Bangladesh had better like equipped in precision ag than India and Thailand. That was very interesting findings from those workshops. And in Vietnam, it was great that like the agriculture minister of Vietnam also dropped by that workshop when we were working on that. Next. But what main aspects we are looking was that everywhere we talk about that the technology in developed countries is not same in developing countries. So that was theme of those workshops. But what we looked into is that concept behind the technology will work, but the technology can be developed locally. So that's what we came up with, and then subsequently I also moderated one open forum in ASB, and one of those open forum in Stellenbosch, South Africa, Dr. Indramani was also there, that precision ag is a data-based decision-making things. It's not the technology. So the concept behind any aspects can be transferred. The technology can be developed locally. So that's what I just put one, what CDEC in India was doing machinery. Next.
Next, please.
Next. It's mostly workshop, workforce development is necessary along with the technology for locally resource. So this I just was looking for what India has been done. So this is one of the things that app CDEC has developed. So those things can be used. Only thing, it cannot be more piecemeal basis. It should be more part of a system that what you need in the beginning to get into this and what the information can be used for what purpose. So if we can use those kind of things and develop the technology locally, that can get more work done than getting the technology from developed countries. Next. So what information we can get from this developed technologies to our so just if we know, use our own information, what the farmers have been doing. If the farmers use information, free satellite maps or whatever he knows about the farm, or go around the farm during pre-harvesting time, before harvesting, or look at what's going on. He can take a notebook and note it down and use that for application of fertilizer or application of irrigation or seeds. Next. So in most of the extreme cases, like if he has like 1 acre or 1 hectare of land, what you can do, you cannot buy high cost technology on, but you can use your eyes, you can use your knowledge as a data. Just go around the farm, get all this information, note down. I come from a farming family. I could see that I have never seen that my father has noted down all this information about the farm. I used to go to the farm and use the hull like the bullock carts, plows, but we never use or discuss about what's going on, or would never note down information. So if we can note down those information, that can be used as data. If we walk and we do crop scouting, yield monitoring, that can be done by hand. I'm talking about the extreme cases, small farmers. That can be done by a paper map. And if we use this information and we can get this yield map, which can be used as a prescription map. So those are some of the things we can use, and definitely the big farmers who have lots of land can use all the technology available on the land. So we have in between mostly, so we can get this slope from the 0 to 100 in India. Next. So definitely we have all the benefits of information. You can use reduction in fertilizer, all these resources can be optimized. And on top of that, there is a climate change things we have been talking about with this lockdown. Everybody's seen that lots of good air, and we can see, we can do that in agriculture itself without getting into the lockdowns. So we can see plenty of, because most of the chemicals are unused, getting into the pollution. If we use it optimizedly, all the chemicals are used, then there is no pollutions. Next. And there's an estimate from USDA that if only 10% farms in US can use precision ag technologies, and 16 million gallons of fuel and 4 million pounds of insecticides, 2 million quarts is close to liters of herbicides can be used.
Dr. Bora.
Yes, please.
Can we finish in 2-3 minutes?
I'm done.
Yeah.
Just
Thank
last,
you.
I think it would be last.
Thank you very much.
Next. Next. So this is this is my last, I just wanted to, what population has increased over the period of time. We are now feeding 7.8 billion people. And this information you can get on the, I normally put just 1 hour before the presentations, this number. We are going into 7.8 billion people. Next, there is one more table in the side. If you see this one, and most of our, including me, between 60 and 65, 70, there are 3 billion people, and now we are 7.8. almost 3 times we have seen. So we need technology or maybe third green revolutions to feed these people. And with that, I'll take any questions you have.
Thank you, Dr. Bora. It was very interesting topic, and we are all very happy to see you talked about standardization in aerial spraying, and that's what we are. I think last 2 ISAE meeting also we were talking about the topic. I'll take a question now from the question and answer. Somebody wants to, I think Ravi Kumar Kaloji, he wants to know what is the power capacity of the UAV, the engine. What is the capacity?
So normally it goes by what size of UAVs. And for small ones, it's about it can fly about 30 minutes. But the big ones, they can go for 2 hours. We talked about that's IC engines. It's not battery powered. That was by Israel Defense Department, which sent the UAVs, and that can go out of sight.
Thank you. We have engineer Dilip Kumar Kushwaha. Can you ask the question fast?
Sir, my question is that just for information, how much time the developed website takes to process the data, and whether it can be used for other application as a raw data?
See, right now we are using the data processing day by day. All the day you take the information, put it there. It takes about a minute to get a 1 day of data processed. The next big question is how do you use that data along with other days of data? So more data you have, more time it takes. So it takes about 1 minute to process about say 3-4 gigabytes of data.
Thank you. We have a question from Rabesh Maiti.
Yeah, Dr. Bora, quickly, you have told a lot about plant using US. Is there any work going on for soil properties and moisture? The same process?
Yeah, some of our colleagues are working on that soil properties, but they have not got quite a bit good success on that. It's because the soil properties, especially moisture, use a thermal camera to see how it goes. Thermal cameras are still kind of shaky grounds right now, not only very costly.
Thank you.
Thank you. Dr. Indramani, Professor Ganesh Singh has to talk, please.
I just have a suggestion because Ganesh, you work with Devin Barua at Tejpur. Can you connect these people with the CIAE, Dr. C.R. Mehta, so they know what has been done? And probably CIA or IRI and other centers should pick it up from there and move forward.
I can definitely do that.
I know you went to Tejpur because you are from Assam, so but let us make it a national project on a wider basis.
No, definitely. I took Tejpur because Devin was my very close friend. That's personal.
I know that, but we have to bring Devin into circuit. He has been outside. He's in the energy group there, and I think Indramani knows him very well, so I should get him in this. Yeah.
Anyway,
definitely, that would be a very good idea.
Yeah.
Thank you,
Maybe
Dr. Indramani.
Next project I'll take with USAID with Dr. Indramani and CIAE.
Thank you, sir.
Very good. Very good. Dr. Indramani, please. Can you thank the speaker?
It was a wonderful day. And we have now, I have to make 2 quick points. One is on UAB, because Government of India has also appointed a committee under the DDG Engineering, and I'm convener of that committee, and have also finalized the report, a recommendation of technical from our side, and submitted to the government, and it is under serious consideration at advanced stage. And we are also going to have, a UAB for pesticide applications very soon. This is one thing, and I discussed with the BIS people and your recommendation on standards. So I will be having that one, use it for our purpose also, and so UAV is going to be applied on the farmers field very soon. And second, for our friends that we are having a similar presentation, more or like from different places. So please try to understand what is our purpose, just to share what is being done at different centers, so we can compare and collect and see that how we have to move. And as Professor Singh said, that through your experiences here in India, Bangladesh, and adjoining countries, and what we have been doing, we can collect that and collate it, and then we can make our own program. So thank you very much, Dr. Bora. Thank you, Sangeeta, for making very good presentation, and thank you, Dr. Syed, for training us consecutively 8th day. And it has been really a very good experience. Tomorrow we have another very good session, and Sibin Raj from Penn State University and Lau from Washington State University. They will also be speaking on automation related, one on water, another on specialty crop. So that will be a very good session tomorrow, and training session, of course. Day by day, we are getting advantage of this one. I was told that now we are more than 1,000 Facebook friends connected to us. Let us make this a very important program. And on last day, we will make this. There has been suggestion that this should not be a spontaneous activity. I'm sure that this is not going to be a spontaneous activity. We will make it a chain activity, and we will see that this activity serves the profession of agriculture engineering in the best possible manner. Thank you very much once again to all for sparing time and being with us. Thank you.
Thank you. Thank you very much.
Thank you.
Thank you, all of you. Thank you. End the meeting, please.